Okay, so good afternoon. In this talk, I will present a joint work with Bruno Galerne and Julien Rabin about an application of semi-discrete optimal transport in image processing. More precisely, we address exemplar-based synthesis of texture images, which consists in taking an original texture as input image. Here, and then producing as output a new image, possibly larger, which has the same perceptual characteristics, but which is not a verbatim copy. And of course, that would be possibly much larger. Okay, and we want to do it quite fastly in order to answer the needs of computer graphics. So here, the strategy that we propose is to begin at the first level with synthesis with a Gaussian model that we understand pretty well now, and apply to this Gaussian model a local transform which actually solves an optimal transport problem. Okay, so in imaging science there has already been many applications of optimal transport. In particular, if you want to transfer the color of one image onto another, it's relevant to do optimal transport in the color space R3. For which concerns texture synthesis, Xia and colleagues have proposed to use optimal transport between Gaussian distributions in order to address dynamic texture synthesis and also texture mixing with kind of Wasserstein barycenters as in Elsa's talk. And also more recently, so there has been another application of discrete optimal transport to texture synthesis by Gutierrez and colleagues. So in some sense, our work is very close to the work of Gutierrez and colleagues, which does structured texture synthesis with discrete optimal transports, but our work is somehow a localized version of there. And so it relies not on discrete optimal transport, but on semi-discrete optimal transport. So in the first part, I will spend some time to recall previously known works about semi-discrete optimal transport that some of you probably know very well. So this problem consists in transporting in an optimal way a source measure which is absolutely continuous onto a discrete measure nu. So actually one theorem that will be of particular interest for us is due to Oren Harmer and colleagues in a paper that deals with least square assignments. So this theorem formulates, as we will see, the semi-discrete optimal transport problem as the maximization of a concave function. And later, several numerical schemes have been proposed to solve this maximization problem. So in particular, gradient-based methods, so some relying on Cassey-Newton and Damped-Newton algorithm, and in particular, a probably convergent one in the work by Quentin-Mérigot and colleagues. Okay, so in order to use these gradient-based methods, actually there is one difficulty, is that we have to know how to compute exactly integrals of the source measures over like generalized Voronoi cells. And so in high dimension, that can be quite difficult. So that's why Geneve and colleagues proposed to use a kind of stochastic optimization framework to solve this semi-discrete optimal transport problem in a very general setting. So this is the algorithm that we will use here and what I will recall in the first section. Okay, so the framework is the following one. As I said, we have an absolutely continuous distribution mu with a density function rho as a source, and the target is a discrete probability measure nu, which attributes masses nu j to discrete points yj. And then we want to solve this Monge formulation of the optimal transport problem by minimizing this L2 transport cost, where the minimum is, of course, taken on the measurable maps, which sends mu onto the measure nu. Okay, so a priori, this is an infinite dimensional problem, but what's nice in the theorem by Oren Hammer and colleagues is that it can be recast as a finite dimensional optimization problem by considering particular mapping T. So these are actually built as weighted least square assignment with this formula. So this formula, given a set of weights V, so there has many weights, there is as many weights Vj as discrete points in the target measure. So given weights, we are able to build almost everywhere this mapping TV. So we just do least square assignments, but with some bias. So of course, if you take V equals 0, you get back the usual nearest neighbor matching, which is already very used in the texture synthesis community. And now if you look at the pre-images of the points yj by these mappings TV, we get generalized Voronoi cells, which are called power cells, and defined in this way. So of course, if you take here, so here is a diagram of a semi-discrete transport problem. So the source measure is in grade level, but what is interesting for now is the discrete target measure on the 5 red points. So these cells for V equals 0 are actually exactly the traditional Voronoi cells. But now, when we put some weight in the comparisons, it allows to move the boundaries on the Voronoi cells and to get these power cells. And what we will see is that solving the optimal transport problem consists actually of moving the boundaries of the Voronoi cells so that the gray measure in the source distribution actually equals the discrete target measure of the corresponding points yj. Okay, so another example in one dimension that we use for numerical evaluation of the algorithm in a few minutes. So here we want to transport a simple normalized Gaussian distribution onto a discrete distribution which is uniform on the 12 blue points below. And as you can see, we have drawn in blue the boundaries of the Voronoi cells, so the cells with V equals 0. And in the upper part of the diagram, we have drawn the boundaries of the optimal power cells. So what is nice in one dimension, as Elsa mentioned, is that we can explicitly compute the solution of optimal transport relying on cumulative distribution function. And so we can also compute the optimal power cells and the optimal power weights. Okay, and so as you can see here, the optimal assignment, which is drawn with plain line, is quite different from the usual nearest neighbor assignment that you can see with the dashed lines. Okay, so what I was saying is made precise by the following theorem, which is already quite old now. It's that a solution to the semi-discrete optimal transport problem is given by a weighted nearest neighbor, a weighted least square assignment TV, where the vector of weights V is a maximum of this function capital H. So we can actually show that this function H is C1 smooth, and we can explicitly compute its gradient. So as you can see, the derivative with respect to Vj is the measure, the mu measure of the power cells of Yj plus the target measure of the point Yj. So since this function is concave, saying that V is a maximum is equivalent to say that the gradient vanishes. And so it means that for each j, nu j equals the mu measure of the corresponding power cells. So this means that the image of mu by the assignment TV is actually nu. So that's why we have this corollary there. So it's really a problem of splitting the mass. So that's why in this simple Gaussian example, since we have a uniform mass in the target, we have to split the Gaussian into equally weighted cells. So now in the gradient, as I said, you have the mu measure of power cells. So Bruno Levy and Quentin Mérigot were able to give some examples of source measure for which we can compute the integral exactly in 2 dimensions and 3 dimensions in a very efficient way, and so to use an exact gradient ascent scheme to maximize h. But now for general density function, in high dimension in particular, it can be quite expensive to get exact values of these integrals. So that's why we can use Monte Carlo method to approximate these integrals, and in some sense it amounts to use a stochastic optimization framework to maximize this function h. So we reformulate just the integral in capital H by an expectation, and so you can use the usual first order stochastic scheme which is written here. So we have iterates v tilde k, on which we take gradient step with step size 1 over square root of k, and after that we average all the iterate v tilde k to get vk. And at each step we need a sample of the distribution mu. And even if the function h on which we take the expectation is actually smooth, or at least C1 almost everywhere, we are still able to get the usual convergence bounds on this stochastic gradient ascent in log k over square root of k. Okay, so what's nice with this algorithm is that it can be expressed in any dimension, provided that you know how to sample from the source distribution mu. But now, when we try to use it in practice, we observe that it converges, but it converges quite slowly. Even for the simple example that I've shown you in 1 dimension with the Gaussian to the discrete uniform distribution, so on 10, 100, and 1,000 points. For 1,000 points, you need 1,000 iterations. For 1,000 points, you need 1,000,000 iterations to attain 10 to the minus 2 relative error on the weights. And it gets actually even worse with the dimension. If we use another simple case of optimal transport with a number of points which is nearly 1,000, so it's fixed in the target measure, then you can see that the convergence gets worse when the dimension increases. It still converges, which is nice, but it needs actually quite a lot of iterations. But anyway, so in this second section, I will make a connection between this semi-discrete optimal transport tool and, by example, texture synthesis. So since the seminal work by Efros Liang, which broadly speaking shows that we can synthesize a wide diversity of textures by kind of simple copy-paste operations, there has been many improvements of this first patch-based method. So maybe you probably all know that, but a patch is a sub-image of fixed small size of an image. So here are 3 patches of size 11. And so patch-based methods have had quite a lot of success in computer graphics, and until the state of the art in 2016. So now, but yeah, one drawback of this method is that there is not really a global description of the synthesized random field. So one drawback is that we have only weak statistical guarantees on the random field that is synthesized in the end. And so that's why we try to use optimal transport local transform in order to get back some statistical guarantees in the patch space. So it was inspired by the paper by Varma and Zisserman on texture classification with textons computed in the patch space. And also it can be seen as a very simplified version of texture optimization, but with weighted least squares assignment. So as I said, on the first level, we perform synthesis with a simple Gaussian model. So if we have an original texture image U, defined on a discrete rectangle omega with values in RD, so D equals 3 for color images, then we can sample the following Gaussian random field, which is obtained as so the average of the pixel value plus the convolution of a normalized Gaussian white noise with a normalized function, a normalized version of the initial image. And So it's quite surprising, but with this simple model, you can actually synthesize every macro texture microtexture that you know. So these are textures which are actually not very structured. So this is nice because it's a random field that is defined on the whole discrete plane Z2. We control its first and second order moments, and besides we can sample it very efficiently thanks to the fast Fourier transform. Okay, but now the problem is that with this model we cannot reproduce some geometric structure of the texture. So it works only with very unstructured textures, because the geometric structures will be more encoded in the Fourier phase information. So in order to add a bit of structure in this random field, we propose to use a local transform in the patch space. So we extract all the patches of the first level synthesis big U. So we look at the restrictions on all the space x plus omega. So we get transform patches px, and after that we get back an output image by simple averaging of the values of x in all the patches that overlap the pixel x. And so now the trick is to choose a map T which solves an optimal transport problem in order to get back some statistical guarantees. So notice that here the map T operates in the patch space R capital D, which is already of dimension 27 if you consider patches which are 3-3 color patches. Okay, so it's a quite challenging framework for semi-discrete, at least for optimal transport in the semi-discrete setting. Okay, so the problem is to here to transform the Gaussian patch big Q in order to get back in the end we will try to reimpose the empirical distribution of the patch of the exemplar. So we use an optimal transport between the measure mu, which is the probability distribution of a Gaussian patch of big U. And as a target, we consider the empirical measure of the patches in the original texture. But actually, to keep only a reasonable number of patches, we extract only 1,000 patches in the original texture. And so after that, we solve an optimal transport problem written here with weighted least squares assignment. And as I said, the weights are obtained with the stochastic gradient ascent. And so at each step, we have to sample a patch according to the Gaussian distribution mu. And yes, in the Gaussian model, we have an explicit expression for the covariance. So the covariance of this model mu is actually the covariance of the patches of the original texture. Okay, so this model is interesting because it has some statistical guarantees. So first, with the first level of synthesis, the Gaussian model respects the frequency content of the original texture. So even after local transformation, we still have some medium range correlations of the original texture. And besides, since we applied the local transform on each patch, we are able to get back some statistics of the patch distribution of the exemplar. And besides, we have a quite simple proposition, but still it's interesting because it gives a guarantee of innovation. So this proposition actually means that if you look to parts of the output random fields which are sufficiently far away, then they are independent. So it's actually a guarantee of innovation for this synthesis algorithm. So now we see here some visual results of synthesis. So of course, with this model, you will not synthesize very, very structured textures. It's a simple extension of the Gaussian model, but you can see, so here, for these textures, the Gaussian model actually fails, but with another local transform, so he's either the optimal transport one or the nearest neighbor one, you are able to reimpose some geometry of the initial image. And actually, the optimal transport transform is able to do this with a kind of statistical consistency. So here, in particular, we get back in a more convincing way the color distribution of the exemplar. So when we have a density of points like this, we get back the true density of points. And after that, we also solve some symmetries of the Gaussian. So we break the symmetry of the Gaussian synthesis. So it's important when you have some textures with shading effects like this one. But of course, when you have very structured textures, like this one with stacked objects, this model will fail because the patches are not large enough to get the geometric structure of the exemplar. Okay, so now to confirm intuitively this framework, so we will try to see that we have indeed better preserved the patch distribution than the nearest neighbor. So actually we have to visualize distribution in a space of dimension 27, which is a bit tricky. So what we do is that we compute what happens on the principal components in the patch space, and we compare the distribution empirically on these principal components. So in black, it's the distribution of the exemplar image. In blue, it's the distribution of the transform patches. In green, it's the distribution after the average recomposition step. And in red, we have the distribution obtained with the nearest neighbor. And so what's important to see is that even if we cannot prove that the average stochastic gradient descent has fully converged in this high dimension, still we beat quite obviously the nearest neighbor assignment. So it's true on many principal components. And also, it's a bit surprising, but still, it still works with larger patches, and in particular, patches of size 5, which is not sufficient, but still interesting. We are able to improve conveniently the nearest neighbor assignment, even for patches of size 5. Okay, so of course, it's interesting to work with larger patches because it allows to capture larger structure in the input image. So here we get the points in a slightly cleaner way. But after that, 5 is not sufficient for this paper image, for example. Okay, so to conclude, one main message of this talk is to say that using a semi-discrete optimal transport tool is a kind of economic way to improve some patch-based methods. And in particular, here we did it with a simple extension of the Gaussian model, but it's a very economic way to gain statistical guarantees in a patch-based method. And actually, we did it with the Gaussian model, but probably that we can improve several other patch-based methods with these tricks of adding weights in the least square assignments. Okay, so now for future work, so it would be interesting to improve the stochastic optimization framework in order to fasten the convergence and also to have an algorithm which better scales with the dimension. And so a promising direction of research on which we are actually working right now is to extend this model in a multi-scalar way. So in order to deal with 3 patches, but at different scales, in order to retrieve better geometric, larger geometric structures of the original. And I think it will be a very interesting synthesis algorithm because one main advantage of this approach is that we can compute all these patch-based operations in parallel. So it's very, very fast. And in particular, the memory footprint is quite low compared to the recent methods based on neural networks. Okay, and now, as a long-term goal, it would be also interesting to extend this framework to continuous optimal transportation because it would allow us to work with GMM models for the patches, which is a quite fashionable way of modeling the patch distribution in image processing. Okay, so I thank you for your attention, and I would be glad to take your questions. Thank you.
Thank you very much. Are there any questions or comments? Yeah.
So what is the metric you're using on the patches? So it's L2 metric?
Yeah, L2.
And so does it make would it make sense to use some other metrics or to estimate the metric?
Yeah, it's a question that I get a lot, especially with Alain Trouvé, which is 10 meters from me every day. Yeah, I thought a bit about that. My opinion is that with 3-3 patches, it makes sense to use the L2 distance between, because there is not much geometry in very small patches. We also tried to use simple variants, so the L1 metric or L infinity metric. Actually, the problem with L1 is that, in some sense, it does not comply well with optimal transport, because sometimes for the L1 optimal transport, for example, for color transfer, you would have some. There is not unicity in the solution, and you would have color inversion, things like that. So L1 is discarded. L infinity does not seem to perform well because it's too sensitive. But now, yeah, it would be interesting to adapt that with a proper geometric way of modeling the patches. It's a very interesting direction of research. So there is a paper by Gabriel Perret about geometric modeling of patches. According to me, there is still some things to be done on this subject, and in particular, yeah, using the optimal transport framework that was developed by Marigot and colleagues is actually available for manifold measures, or actually measures defined on manifold. So yeah, it would make sense to extend this construction with a metric which is let's say better sensitive to the geometry. But defining a geometry on the patches of an image does not seem a trivial problem to me.
Yes, and my second question is, do you need to have renormalized densities? So you're really working with total mass 1 densities, so probability densities.
Yeah. And
you don't need to have.
Yeah. So yeah. Here, so yeah, you're referring to your work with Lena Ikshiza about unbalanced.
Yes, I want to see if it could be applied. Yeah.
Yeah, here we have a kind of probabilistic modeling of the distribution of patch.
Okay, that makes sense. Okay.
So yeah,
okay.
I don't think it would be applicable here. Yeah, thank you.
Thank you.
But for color transfer, I think, which is another problem, applying unbalanced optimal transport would be interesting. Okay, so yeah.
Okay, just one question. So the space of patch is high dimensional, but in practice, your point set is much smaller.
Yeah.
And
it's not so. I guess for 3-3 patches, it's not so smaller. I think,
okay,
because there is some noise and
as the dimension increases, you can expect that there is a limit dimension for your point sets. Can you exploit this in some way, or?
It would be interesting to extract some submanifold structures in the patch space, and so so Alain Trouvé proposed some methods to extract some submanifold structures in these spaces, and yeah, it would be interesting to look at that. Yeah. Thank you.
I just had a small question concerning your example with the kind of red flowers. So you say it was not so satisfactory.
It's papers, yeah. Papers, yeah. Yeah. So here it does not do what we would like it to do, but so it reimposes a little bit the color distribution, but it is not sufficient to reimpose the geometry that we would want.
Yeah.
And the problem is that we would have to work with larger patches or in a multi-scale way.
Okay. But that's one of your perspective. That's what you
okay.
Do
So
you have some hope?
Okay, we are working on that now, and so here is one result that we obtain in a multi-scale fashion. Okay. So here, as you can see, we get back some weird peppers, but still we have something which is much better than in the monoscale synthesis.
Yeah, sure.
Okay, so this example has been computed in about 20 seconds with an unoptimized MATLAB code.
Okay.
So yeah,
So that's tractable. Yeah.
it's interesting. Yeah.
Okay. So if there is no question anymore, thank you again.
Thank you.